Hi everyone, I'm Sergio. I am an engineer from the Robot Manufacturing Unit Department at ITRI. Today, I will talk about our intelligent robot vision systems and meta factory developments. I'm going to introduce to you two key products developed by our department, which are RobotTwin and FO Vision. Nowadays, in the context of global connectivity, an increased demand for efficiency and an accelerated production pipeline, businesses are making their physical factories to be described entirely in terms of software. No matter where users are located around the world, with the aim of 3D digital environments, virtual reality deployment, and a communication scheme between digital and real assets, users can perform sensitive operations in the digital world and bring optimizations to the real world. This is the idea for MetaFactory, which serves as a realistic virtual environment replicating actual factory layouts, robotic cells, and workpieces. Along with virtual reality interaction, real manufacturing sites can be completely software-defined. As a result, users can navigate all the way through the virtual scene and test sensitive operations safely. More specifically, RobotTwin, as part of MetaFactory, intends to link motion commands between real world and virtual scene. Users can deploy robot actions back and forth and collect relevant data from the real world to the virtual scene. The purpose of RobotTwin is to achieve paveable human-machine cooperation by connecting VR equipment combined with high-fidelity physical engine from NVIDIA Omniverse, resulting in a human-machine mixed interactive simulation technology. Here we have one video. For instance, the user is wearing a VR headset and also grabbing a virtual stick. Using one of the VR controllers, making the virtual world follow the stick. This action is related to robot teaching. In another case, we have a user wearing a VR headset. Meanwhile, the virtual robot is performing defined motion commands and compounds of data coming from the real world in the form of images, and other graphics are projected into the virtual environment for the user's interest. RobotTwin comes with two operation modes. The first one is known as follow target mode. In this mode, the user grabs the virtual stick and the virtual robot will follow this tool in real time. Therefore, joint states will be shared to the real robot, resulting in real-time synchronization. Robot safety is also considered as well, along with a virtual reset option to prevent both robots from any undesired displacement. One more feature here is that 3D animations of the workers are included in the virtual scene to make the virtual reality experience more realistic. Let us now refer to RobotTwin's second mode, known as play mode. In this mode, virtual robot is given defined motion commands. Those are shared to the real robot to achieve real-time synchronization. At some point, data from the real robot is collected and projected into the virtual robot. This is all part of a loop to simulate a running production line. So now, let us proceed with our second product known as FO Vision. FO Vision mainly consists of three pieces of hardware, which are a 3D camera, a particular lighting source, and an edge computing device. The system will collect light-controlled 2D images along with 3D point cloud data to be processed by an embedded AI object recognition model. At the same time, the system will compute pickable points over the workpieces, and it will command the robot arm with inverse kinematics to perform pick and place operations. As a matter of fact, AI training for object recognition demands reasonable training datasets. Therefore, manual labeling can be tedious and time-consuming. In contrast, FO Vision offers a modeling and automated AI tool capable of mapping real-world 2D images into their workplace 3D CAD model representation. This tool not only enhances the realism of the virtual environment, but also automates the generation of annotated datasets, capturing pickable and unpickable points for each workpiece. To ensure that valid training dataset acquisition is doable, the AI annotation tool makes use of our domain randomization approach. In this way, several parameters will vary, such as workpiece posture and quantity, camera lighting and posture, light intensity and color rendering as well. So here we can observe how the algorithm makes the change in the beam color, and also the objects are placed randomly, and they all have variations which will make the training dataset stronger. So with all this being said, let us observe FO Vision deployment. Considering a real working environment, FO Vision collects data from a container loaded with metallic pipes and commands an industrial robot arm. The synthetic training dataset generated to train the embedded AI object recognition model proves to be valid in this case. So here we observe the objects loaded into the container, and then we can see the masks obtained by the AI object recognition model. And all of this is the result of the trained dataset, which has the variations mentioned before. So this is all for my presentation, and I thank you for your attention.
Thank you, Sergio, for such an insightful presentation. Concerning your topic, we've also received some follow-up questions via email. So the first one is, how many configurations can FO Vision be deployed in?
Hi, thank you for the question. Let me reply right now. With the FO Vision, we handle two modes mainly. One is known as in-hand. This is well known in the field of robotics, and in this mode the camera is mounted on the robot's end effector or gripper, and the goal of this method is to determine the transformation between the camera and the robot gripper or robot flange, and here we handle this case using checkerboard. And we have developed our methods to achieve this in-hand calibration. And we also consider the other mode called eye-to-hand. In this case, the camera is mounted apart from the robot, and we also make use of the checkerboard to achieve this calibration. As I mentioned before, we have developed our methods and algorithms to achieve this result. And honestly, we most of time use the FO Vision using the eye-to-hand mode, but we are open to consider other conditions. so we can work with different scenarios depending on the production line, and we have used the FO Vision pretty well recently. Yeah.
Okay, thank you so much for answering. Another question is directed toward the application of Robot Twin, the flexibility and possibility to integrate. Does Robot Twin accept other robots?
Oh, this is very interesting. Yeah, of course, we can integrate other robots into Robot Twin. For this, we have to get a file called URDF, which stands for Unified Robot Description Format. And with this file, we need to consider the robot links and joints and any other relevant information regarding dimensions or some configuration about the robot. As I said before, we have to consider if the robot uses prismatic or rotational joints or a combination of both. Definitely we can make the integration with any kind of robot into Robot Twin, and we can also develop the communication between the virtual robot and the real robot. In this case, I was describing before universal robot case, and in this case we include real communication between the virtual UR10 and the real UR10 through TCP/IP communication, and this is possible to do with any other robots depending on the API of the specific robot. So definitely we can consider more robots, and as I said before, we have to go with the URDF file, and I also need to mention we have to collect the CAD model of the robot, and this file must be with the real units. I mean, with respect to the real robot.
Mm-hmm.
Yeah.
Okay, thank you for such a comprehensive answer. What about if the user wants to use Robot Twin and VR? What are the specifications required in order to adopt this configuration?
Oh, yes, sure. During my presentation, I mentioned that we have developed Robot Twin based on NVIDIA Omniverse, and because of this, NVIDIA has recommended some hardware. For instance, you have to, if you want to make a good setup to load VR functionality, you need to consider a CPU consisting on the Intel Core i7, at least the 9th generation, or you can also go with AMD Ryzen 7 with 8 cores at least, and you have to consider 64 gigabyte of RAM memory, and the storage at least maybe 500 gigabyte. And in terms of GPU, you have to go with maybe RTX 30 series at least, and well, virtual RAM, the GPU should go with 10 gigabyte. This is the recommended configuration from NVIDIA Omniverse to make use of Robot Twin, and I believe it's quite correct. Yeah.
Okay, thank you for your recommendations. And lastly, we have another question. What is OpenUSD, the format behind digital scenes?
Oh, this is pretty interesting. This OpenUSD was developed by well-known animation studios in the world and intends to bring several configurations regarding 3D CAD file workflow, and it's well known in the industry that right now there are several sources to process the CAD files and 3D modeling objects. There is like paid software and open source software, but the OpenUSD brings all of these together, and it has several advantages. For example, it's highly interpolar. It has it's possible to bring different files all together, and it can manage several layers in CAD files. So this allows digital works to work, and it is also possible to collaborate remotely with this platform. You can bring several workflows into one, and I really believe this is a very powerful piece of software which we can understand pretty well, and we use this as part of our development.
Okay, thank you, Sergio, for such a comprehensive sharing. So I think that's about how many questions we can take for now. However, you can continue to drop your questions in the chat function, and we will get back to you after the event. So thank you very much, Sergio.